Hello, everybody. Good to see you all again. I hope that you had a pretty good weekend. It's a difficult time in the world right now, but I will say it's nice to be able to talk to everybody about math. So, one thing I need to do first, I can tell that our audio is a little bit off, so I'm going to take this and mute that. 1 second. Great. Great. So, actually, what I just did is I just finished my class. I was teaching the Carnegie Mellon PhD students and some undergraduate students as well. And so we just switched up the equipment. Now, it's good to see that there are people who are interested in thinking about math today. I also see that people are interested in the green shirt. And I promise you that will come as soon as we put out this thing related to coronavirus. I was actually up until like 5 a.m. last night. I've become a Android programmer. I've been writing an app that's going to be used on all of those Google Android phones. But in any case, today we're going to focus a little bit on math, and hopefully within a day or two, maybe, you'll even find out what else I've been up to. As usual, in this live stream, we're going to be talking about math improvisationally. And the goal is to be able to see what people are interested in, and then to give mini lessons that might tie together a bunch of different concepts. Something that's very important that I've been thinking a lot about recently is what does it really mean to learn anyway? In some sense, we ideally learn not only how to do certain tasks, but how to combine all of the different things we know at the same time. And so this live stream, as some of you have noticed, is not going to do what your teachers are doing, because your teachers are already doing it. They're already teaching you facts, they're already teaching you methods. The goal of this live stream is to give something that you won't be finding in the textbook, and you won't be finding on the test. Instead, we'll just be looking at questions and trying to think. And I'm doing it also as a challenge for myself, because I don't know what kind of questions we're going to get. I actually love the challenge of coming up and trying to figure out what we can do to answer some of your questions. I also have gotten to see through the many other live streams that we've run that the core audience here is around algebra and geometry. And so we're going to be trying to find questions for which I can hopefully answer something that will make as much sense as possible to people who are maybe learning Algebra 1 or geometry. So let's see. What can we get here? Can we get any interesting questions? So I'm looking to see, we have different sources of questions. We have our moderators, which are providing various questions to come forward. And also I can see that there are questions coming right in front, like Paperboy saying, Po-Shen Loh, hi. Hi, Paperboy. Paperboy. I wonder if I can make something that's related to paper. When I think about Paperboy, I honestly think about how you try to deliver things in as efficiently a way as possible. And there was something that I had realized when I was, not realized, maybe I found it by accident. I'll show you this. This is kind of cool. So have you ever, looked at a map before? And if you look at a map, and the map looks like this, I don't know. Maybe it looks something like this. I don't know if this will work or not. Oh, I want to make it a little bit more complicated. Let's do this. Okay, so this is a map. I'm not saying that this is any particular picture. This is maybe like a map of the neighborhood. And these are roads. Like, these are actually roads that you have to bicycle along. I don't know if people here still deliver newspapers by bicycle. Actually, maybe this is an old school thing. Nowadays, everyone reads the newspapers by just going to the internet. But anyway, long time ago, you had to actually go and bicycle along this and deliver all the papers. By the way, it's not possible to bicycle around this whole thing and go across every road exactly once, Watch. Let me try. Let me try. Suppose I do that, and then I do that. Uh-oh. Maybe I'll do that. Let's do that. And then here. But now I'm in trouble. I want to go through every road exactly once because I'm the paper person, the paper delivery person, and you got stuck. You got stuck. This is just so annoying. It's so inefficient because if you're doing this paper route, you got to deliver the newspapers on this road too, right? The deal about delivering newspapers is you actually have to go along the road and deliver the papers, right? So that's no fun. And then you have to go and bicycle all the way back, and you waste all of that time that you could have spent, I don't know, going home from school early. So unfortunately, it's not possible. You got stuck. And indeed, somebody made a comment. Somebody said there are too many odd nodes. So this is a topic in graph theory and combinatorics, which is an area that I teach in the university. And somehow the situation here is the reason why you can't go through every road exactly once is because look at this place here. This place with 3 things. You see, this thing has 3 roads coming out. And at some point I go in. And if I go in, I gotta go out. So that's gonna eat up an even number of roads coming out of here. So actually, if I just look at any intersection, suppose I had some map, and the map had a 5-way intersection. If you're a city planner, please don't do that. This is a huge pain if anyone's trying to drive or bicycle and get through this intersection. But anyway, if you see this kind of a thing, you know, as the paper person is coming through and delivering papers, maybe they come through, in and out, and then they do la 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 something else, and then go in and then out, and you're in trouble because when you go in, you're going to be stuck. And so the problem here is the reason why you can't go through all of these roads as a paper delivery person is because here's the intersection with 3 roads coming out. So that won't work because if there are 3 roads coming out, the only way to deal with that is either for that to be the beginning or the end of your route. But how many things have an odd number? 1, 2, 3, 4. I have 4 intersections with an odd number of roads coming out. And there's no way for me to use all 4 of them as beginnings or ends of my route. Okay, so unfortunately, this is showing that paper delivery is impossible in a general city. But that's not true. Actually, there's something nice about paper delivery. Again, I don't know how many people here will think about these kinds of things, because these days you just look at the news online. But if you do this, let's just draw it a little bit simpler. There's something important to know. When you have a street, there are usually houses on both sides of the street. Wow, I see there's a question from myself. Königsberg Bridge. So first of all, I'll have to disclose that is not me. You have seen me. I am talking to you. There's no way I could possibly have typed that in the chat. So it appears that there are people all around the world who are starting to go and use my name. Okay, well, I'll just say that was fun. In any case, though, Bridges of Königsberg is what this person had said. And this particular person was, whatever the person's name is, was referring to the fact that there's an extremely famous problem about this, where somebody was trying to go across all the bridges in a city called Königsberg, where you only went over every bridge once. However, I want to emphasize that delivering newspapers is a good situation. Because when you deliver newspapers, the way you actually do it is that there are 2 sides of the street. And in fact, the usual way that somebody might deliver papers is maybe go along the side of the street and throw them all in one direction. Because you know, like if the street has 2 directions, it is not very safe to go bicycling and then chuck these papers way over, like, possibly hitting cars or something. Instead, you usually go along the sidewalk. So if you go along the sidewalk, suddenly you can do this. Watch. Oops, I want a different color. Let's just go. I'll go along the sidewalk. When I say I go along the sidewalk, what I mean is I can go over every single road twice because there are 2 sides of the street. I hope this will work. Let's go. Let's go. This might actually work. I hope. We'll find out soon. As you can see, I'm trying to be the paper delivery person, going across all the sides of the street. It's actually going to work. Wow, it worked. So this is very nifty. This is very nifty. The idea is that if you do paper delivery, because there are people on both sides of the street, there are no odd intersections. Every single intersection has an even number of roads coming out of it because it has an even number of sidewalks. You know what I mean? It's like along the road, there's like 2 sidewalks, so you always get an even number. And there you go. And Philip Neller says, my dad was a paper boy. Actually, paper boy, when I was growing up, was a thing that many people did after school. They would like come home from school and they would do their job as the paper delivery person. And so paper boy's user name has made me think of this like fun math fact, which is that, no, you cannot go over every road exactly once. But if you're a paper delivery person, it's okay because you need to go over every road twice. And you can always do that. Okay, what else do we have? Let's see. By now, maybe we've seen some questions pop up in the chat. Let me see. I see that there are a lot of people imitating me. So I will say, in this particular situation, it's pretty clear that those are not me. But I have heard that somehow now, all of a sudden, all over the internet and all of these other like online math classes, there are people who are calling themselves Po-Shen Loh too. That's a little bit harder for me to show that it's not me. Although I'll say that whenever there's like 5 people who are all called Po-Shen Loh, it's probably clear. It's probably clear that they're not all me. Okay, let's see. What else do we have? Whoa, interesting. Athena Wu asks, what math should someone take after they have finished all the math classes in their high school, like at a university? I'll say this. It's okay to take a math class at a university if you're done with all your classes at your high school. In fact, I did that also. And those are the classes that I learned the worst. What do I mean by that? Well, when you're a high school student, you actually have a pretty busy schedule. High school students usually take like 6, 7, maybe even 8 classes. And also usually those are all in places where you can walk from one classroom to the next in a short amount of time. Your university might require you to drive half an hour to get there. And also the schedule of the university is usually not the same as the schedule of your school. And people in college might only take 5 classes at a time. So I'll say that those are classes which I eventually even retook. I eventually retook them and understood them even better. That said, I'm not saying don't go to university. It was still a good experience. It actually showed me what a university class was like. But I'm just trying to emphasize that your goal in life should not be to try to get as fast as you can through all the classes that are officially offered and then run into the university thinking that's going to teach you everything. It's actually not necessarily going to. You will learn something from that. But in fact, what you'll learn even more from is from self-studying or from using your spare time to do some really hard questions. When I was in high school, when I was in high school, I would spend any extra time I had really trying to think about some hard questions. That's, for example, why we even made this daily challenge. Like, I'm referring to the daily challenge online course, not the live stream. But we actually thought it was important to make it so that everyone can actually engage in some hard math, where you go and think about problems that you have no idea how to solve. That's actually what you should be doing, in my opinion. So what I generally recommend is don't necessarily speed through your courses in your school. Take them at maybe a little bit faster pace if you want. But it's also fun to learn from teachers. I learned from teachers how to explain things. I think that's pretty interesting. And at some point, yes, you'll go to take some classes in college, but don't let those make you think that you're really smart. That's not the point. You use those to maybe get a different view on math. And it might even be later on that you'll retake those classes again later. So if I were to go and summarize my opinion about learning, it's that if you are in a situation where you've gone faster than what you have available in school, it can be beneficial not just to go fast through the normal classes, but then take a step back and try to think about whether there are harder things to do. For example, there's more than math. In fact, when I was in school, I was writing a lot of computer programs. I was writing video games. That has come in extremely handy because on this coronavirus project that we're doing, even though I was the mathematician, I sort of have found myself in the middle of the whole guts, the heart of what makes our app work. And in fact, at this point, I'm the guy who has to try to think through every single step of how you make a mobile app do things that you might not have expected before. And these are things that I never learned in school. I never learned them in college. The only way you learn is by messing with it yourself. Okay, more questions. Yes. Yes, Yihong Lee says, help stop coronavirus. We are on it. You will hear something very, very soon. How to calculate mass of the Earth. Oh, that's interesting. Mass of the Earth. If I wanted to do that, what would I do? That's a pretty good question. So I like this question. So at this point, if I want to calculate the mass of the Earth, so by the way, I have no idea. The thing could be completely off. But now I'm kind of curious, okay? So if I have the mass of the Earth, how do we start? I want to start from something that I already figured out before. Yes, Ron Yoder says, here comes a Fermi problem. And I'm going to tell you, I could very well be wrong, okay? There's no guarantee that this is going to be right at all. But I'm going to say there was a starting point, which is that I know the volume of the Earth. The volume of the Earth, what was it? Did anyone remember? Was it like 200 million miles? Cubic miles? I already forgot. Was it 200 million? What did we have last time? So we had figured out something last time, and we could work it out. Some people are saying 260 million. Oh, is it billion? I just want to make sure I have the right number. Was it billion? If it was billion, it was times 10 to the 9 miles cubed. Okay, great. So we had about 200. And people say it's about 260. It's okay. We'll use about 200 billion. That's close enough. Okay? And the first thing is that we want to convert this into something that's easier to use, because if I have volume and I want to get mass, clearly what I should use is density. And the thing that is useful for density is to use the fact that in metric units, density is nice. So in metric units, if you remember, we actually came across this in a live stream as well. There's something called water. And the density of water is, if you have, oh my gosh, what does this look like? This is clearly a liter of water. As you know, everyone carries water in like rectangular prism boxes, right? Anyway, I'm going to call that a liter of water. This is 1 liter of water. And that's 1 kilogram. Okay, well now I need to go and turn this thing into something about miles. How many liters are there in a mile, in a cubic mile? Oh no. So I guess I need to convert all of these into other units, which is like meters, right? So if I've got liters, what's a liter in terms of meters? I guess I need to work that out too. So let's see. If you remember, 1 liter was equal to 1,000 cubic centimeters. And that was something we also saw last time. And it's actually kind of easy to think about that, because if you imagine your water in a box, what's 10 centimeters? Like this? Something like this? And I could imagine that if I had a cube which was about this wide, this tall, and this deep, that looks like a liter. I mean, all of us Americans say a liter is a little bit bigger than a quart, right? So it's about a quart. A quart's like 4 cups. I could believe that. So let's convert this into meters. So what's this in terms of meters? So this is like 1,000 cubic centimeters. If I want to convert that into cubic meters, what do I have to do? It's going to be 1,000 times the conversion from centimeters to meters is 1 over 100. Except that it's not this. What am I missing? I'm also missing the fact that this is, if I was converting centimeters to meters, I would use a 1 over 100. If I want to do this with cubic centimeters, I better cube that. Okay, so now I know what a liter is in terms of cubic meters. Yes, thank you. Thank you, Andy Yu, for saying cubed. So now I need to divide this. Well, it's like 100 cubed is a million. It's going to have 6 zeros. So this is going to be 1 over 1,000. We usually write that as 10 to the minus 3 cubic meters. Okay, so now I need to go and convert the cubic miles into cubic meters. What's miles in terms of meters? You see, this is where we Americans are using these very, very strange units. If I want to convert miles to meters, what would I do? Anyone have a suggestion? What would I use? Miles to meters. Use calculus. I'm not sure I would do that. But I need to do something with miles to distance in metric. Some people are saying, I don't know. Some people say 5 miles is 8 kilometers. And indeed, yeah, that's right. 5 miles is 8 kilometers. It's oftentimes if you run races, like I don't know if people here are into track, like in high school or whatever, but a mile is about 1.6 kilometers. My equal sign here is approximately equal. Okay, use Google. It's definitely one way to do this. But somehow I don't know if people know this, but like there's a 1,600 meter event. Do you follow this? Like, hopefully the Olympics will happen at some point. But in the Olympics, people run. There's a 1,600 meter, right? Why is it called 1,600 meter? I don't know. Maybe they like 1,600, or maybe it's a mile. In fact, actually, a long time ago, when the British were doing a lot of these things, when the UK, when Britain was one of the countries that was like the center of the world, they were using miles, and everyone was talking about how fast can you run a mile. And so that became a thing that people cared about. Can you run a mile in less than 4 minutes? And so it's quite natural after we switched to meters to say it's the 1,600 meter run. Okay, anyway, let's go and convert this. If a mile is 1.6 kilometers, what's the most efficient way to find a cubic mile? I need to know 1.6 cubed. Oh no, how will I do that? Different people have different ways of doing this. I will tell you what I'm going to do, and that's because whenever I do these live streams, I like to just show you what happens in my head as I combine different ideas from math. When I see 16, I see a power of 2. Because I know a lot of powers of 2, that comes in very handy if you're a computer programmer. In fact, something I was doing for our coronavirus app involved something called the Fourier transform, and I had to use powers of 2 in order to make this thing happen. In any case, as we keep going, 1.6 cubed, I'm going to say, I know what is 16. 16 is equal to 2 to the power 4. It's 2 times 2 times 2 times 2. And so 16 cubed, if I care about 16 cubed, that will be, well, it's 2 to the power 4 times 2 to the power 4 again times 2 to the power 4 again. So it's like I have 4 of the 2's, and then I have 4 more of the 2's, and then I have 4 more of the 2's. That's 12 2's altogether. Now, what is this approximately? I know that 2 to the power 10 is a nice number, because that's one of the core pieces of how a lot of computer things are figured out, like kilobytes, megabytes, and gigabytes. I know some of you actually have taken the online course that we run with Daily Challenge, that you will recognize. It was one of those. But this 2 to the power 10, that's equal to 1024, which is why we often think of 1024 bytes as a kilobyte. Okay, so this is about 4,000. Whenever there's 2 to the power 10, that's already about 1,000. This is about 4,000. And so now I know that at 1 mile, 1 cubic mile, is about 4,000 cubic... Oh no, I missed a cubed. There's been a typo the whole time. I'm so sorry. There's a typo here all the way through. I'm so sorry I missed that. I should have paid more attention to the chat you guys had. Okay, now let's figure it out. It's 4,000. Oh, that's so nice, because I'll move the decimal point. 1 cubic mile is about 4 cubic kilometers. Really? That's cool. I actually didn't know that. Some people say it's 1.96. Are you sure it's 1.96, 4.96? I think you mean 4.096. That's much better than 4.96, because 4.96 is approximately 5. But in any case, so I'm just going to go ahead and use this like 4. I didn't know that. That's kind of neat. I learn something every day. So a cubic mile is really about 4 cubic kilometers? Okay, let's keep going. So now we go up here. Oh, wait, we need everything in meters. So what would I do? If I want meters, it's 4 times what? Cubic meters. I need to go from kilometers to meters. A kilometer is 1,000 meters. So it's 1,000. Except it's cubic kilometers. So put a third power here. Okay, and I put everything together. I get 1 cubic mile is big. It is 4 times 10 to the power 9 cubic meters. Where what I've just done here is I took the 4, and there were 3 zeros, 3 more zeros, 3 more zeros. Yes, temp ID is able to type lots of zeros. More zeros than I can count. So I hope you have about the same thing. What about the decimal point? Somebody asked. Yes, you see, I'm approximating. Thank you very much for asking about the decimal point. I could write 4.096, right? But that's not the point. Maybe I want to understand a little bit more clearly, Philip. If you could maybe explain what you mean by the decimal point, I'm happy to try to address you directly. But what I'm doing is I'm approximating. So I'm looking at, there's a 4, and then there should be like 9 more zeros, all right? So when I put all of this together, what do I have for the volume of the Earth? I guess I have to multiply some numbers. We have to now go and put all of these like exponents together. Oh, that's neat. 2 times 4 is 8, which is approximately 10. So I'm going to get a really nice round number. If I multiply everything together, I need to know a cubic mile times this, so that's the conversion factor, times this thing. And when I put the whole thing together, then the volume of the Earth becomes 4 times 2, which is 800. 4 times 200 is 800, times 10 to the power 18 cubic meters, which I'm going to approximate. 800 is about 1,000. So now what I have is I have about 10 to the power 21 cubic meters. Okay, the last part is how do I go between cubic meters and mass? Well, once I have this, I need to now think about density. Water is 1 kilogram for every liter. Oh, Philip, thank you. I see. So you're asking what did I do with the decimal point? Thank you. And now I understand. It's like, why did I do 16 cubed? I did 16 cubed to get about 4,000. But then because it's 1.6 cubed, the 0.6 is like a divide by 10. Let me just quickly answer that, right? This 16 cubed over 10 cubed is going to be 1.6 cubed. I want this. So that's equal to this 4096 divided by 1000. And that's how I move the decimal point 3 times to get the 4. Does this make sense? Okay. So now we've got all of this, and let's keep going. So now, wow, the world is smaller than I thought. And Joe, the world is actually very small. In my life, as I've started, well, before this coronavirus, when I was traveling all around to talk to people about math, you just get the sense eventually that the world is a really small place. You can go to sleep in China and wake up in San Francisco. And that's how small the world is. Okay, let's see. What do we have here? Let's finish this up. So now the volume of the Earth is 10 to the power 21 cubic meters, about. And now I also know that there's a correspondence, there's a relationship between water. Water is going to be 1 kilogram corresponding to 1 liter. But we know what is 1 liter. 1 liter, we had worked out, was 10 to the minus 3 cubic meters. So now that means I should put this into liters. That would be useful. If I want to put this into liters, then that tells me that this is 10 to the power 18 liters. Where what I've just done is I said a cubic meter, well, a liter is 1 over 1,000 cubic meters, so let's just divide by the 1,000. Okay, now we're almost done. If the volume of the Earth is 10 to the 18 liters, what should the density be like? So here's where I need to think about rocks and water. And this is where I kind of think of my own life. It's like, if I had a liter of water, that's 2 pounds. 1 kilogram is about 2 pounds. If I had a rock, I used to go to the gym. I used to lift weights at the gym. You can't tell anymore. But I used to lift weights at the gym. And at the gym, they were these dumbbells. Or maybe you've seen these dumbbells at home, these metal dumbbells. In fact, at the very core of the Earth, there's a lot of rock. And the rock is, I believe, there's a lot of like molten iron or something at the core of the Earth. So if I'm looking at these dumbbells, it's like, maybe if I had a 10-pound weight, it would be like this big. So in some sense, my way of thinking is that in the amount of space, that's the 1 liter, if I consolidated these weights, I don't know, maybe I could put like up to 20 pounds of weight into that space. I'm just kind of thinking, right? I'm just kind of thinking that somehow in my head, I'm like, it seems like it's about the right order of magnitude, and I could be off by a factor of 10. But I'm just going to say, if I had my water bottle, right, in the gym, when you go lifting weights, you have your water bottle, looks like this. That's a 1 liter water bottle. And that 1 liter water bottle weighs 1 kilogram, which is about 2 pounds. And that seems to be about the same volume as like 20 pounds-ish of dumbbells. Again, this could be way off, but let's see. So that's about the same as like, if I look at the metal from the dumbbells, I don't know if this makes any sense to you guys. This is like about 20 pounds. So I'm going to say it's like maybe about 10 times as dense as water. I could be way off. But I'm going to say if I'm not using water, this is now iron. And this is water. And it looks like I need to times 10-ish. So what I'll say is that if this thing was going to be, if water, it would be like 10 to the power 18 kilograms. And instead I'll say, no, it's not water. Let's say if it's 10x as dense as water, I'm going to give you an answer of 10 to the power 19 kilograms. Okay, time to check the answer. What was the answer? Oh no, this was way off. So the answer was 10 to the power 24. Is that right? Not 18? Okay. So in that case, what this shows is that, yes, there are a lot of different materials in the Earth, Philip, you're right. So what this is showing that somehow the mass of the Earth, we're off by like 10 to the power 5 orders of magnitude. So maybe that wasn't super, super close. But let's see, where could that have gone wrong? I'm actually curious now. So you're right, there are a lot of different materials in the Earth. I have a hard time believing that those materials in the Earth are like 10,000 times as dense as water, though. So that's probably not where things went off. Instead, possibly where things went off. Now I'm actually kind of curious. Was everyone following the different... Somebody said 10 to the 24, not 10 to the 18. Oh, yes, thanks. You're fixing it. What you're saying is that I did the math wrong. Yes. No. So somehow like cubic meter should go the other way around. That's why everyone's talking about 10 to the 24th. And here's what you're finding out. You're finding out that, you know, a mathematician and a scientist is really lousy at arithmetic. This is a true fact. In some sense, the worst person to ask to calculate a tip is a professional mathematician, because they will just say, you could figure it out. No, this is wrong. The reason this is wrong is because a cubic meter is 1,000 liters. Thank you all. Let's fix that. 18 becomes 24. If that's 24, if I use normal water, what would I get? I would get 24. But I'm using 10x. If it's 10x, I get 25. Could someone please repeat what was the answer? Actually, what was the actual answer? Again, the chat goes so fast that I missed it. What was the actual mass of the Earth? I saw that somebody wrote in the chat that their teacher asked them to memorize it. Oh my gosh, that was amazing. This works. Bam. So there's a reason why, wow, we've got lots and lots of Po-Shen Lohs here with lots of different spellings. But what I'm seeing, I see like 5 times 10 to the 24. We got so close. I'm amazed, okay? And now I want to tell you why I did a few of those calculations that I did. You see, I knew that I made a math mistake. You know, I could have just said, hey, it looks like we're just way off. I guess the estimate didn't work. But what was going on in my head as I was saying, how in the world could I be off by 10 to the power 6, is where would that come from? You see, that's the beautiful thing about math. With math, you can figure out if something's not matching, where did it break? You see, I went back to look at my assumptions. I was thinking in my head, like as I was doing all this, I was like, wait a second. We know that that's almost right. We actually know, according to the internet, that it's about 260 billion cubic miles. So the error I could have gotten from here is not more than an error which is like 25%. That's tiny. And what that means is after I do all of these calculations, which are dealing with exponents, actually the final number that I got here of this 10 to the 21 cubic meters, that's not very far off from the actual volume of the Earth. The only place that I made some approximations are like this 1.6 cubed, and that's not much of a mistake. That's like 4096 to 4000. I care about multiplicative errors, like how much I multiply by percent errors. That's like 2% error or something, or maybe 4096, yeah, about 2% error. On the other hand, when I finally go and put them together, I went to the 800 and I changed it to 1000. So in fact, what you've just noticed is that the two errors canceled each other out. That's why Fermi estimates work. You see, in Fermi estimates, what I did is I said, well, it looked like 4096, I'll call it 4000. I rounded down. And then I took the 4 and I multiplied by 2, I got 8. I said, let's round up. The way you should think of this is that as you're rounding down and up and down and up, your mistakes sort of wipe each other out, in the way that if you're just kind of randomly walking back and forth, you actually kind of go not too far. This is actually something from statistics. It's something from probability theory called random walks. You do go far, but only after you take a lot of steps. So basically, when we did this, I was like, in my head, when we got this final answer, I was like, what in the world's wrong? I know that I made a mathematical calculation error because this volume of Earth is supposed to be right. I've at most a mistake of a factor of 2 up there. If that's the case, then that's telling me that there is an object which is like 50,000 times or like 100,000 times as dense as water. I have a very hard time believing this. And the reason I have a hard time believing this is because now we start to think, what is water? What are solids? You know, like you're basically packing things together. This is now chemistry. This is like talking about chemistry and physics. You see, if I have like a gas, that's something where you have a very low density because you have all these particles and they're like bouncing off of each other. But what's special about a liquid is that in a liquid, the particles are kind of just rubbing against each other. And in a solid, they're more efficiently packed. Okay? So somehow the density of water, that's already packing together a lot of atoms and molecules. At this point, then you start to think, what is causing different atoms and molecules to have different weights? Well, one is like, how closely together can I put the different atoms and molecules? But you probably can't get much, much closer together than like the hydrogens and the oxygens of the water. Then the next question is, well, what is an atom? Some of you have seen pictures that look like this. People have seen these kinds of pictures before. So if this is what an atom looks like, actually the idealized image of this is that there's a nucleus, which is very small in the middle. And then there's like these electrons which are going out and about. And then these atoms kind of bond to each other based on their electrons. This is a bit of a chemistry lesson. But somehow you have the electrons like this. And then the atoms interact sort of out by the radius of their electrons. That's sort of what's going on. And now, when you look at this, you're like, well, how could I have significantly bigger density than an oxygen molecule? An oxygen molecule, is there anyone here who has taken some chemistry who knows what is oxygen? Oxygen in this thing called the periodic table. In the periodic table, you'll see something like this. O. There's some number next to it. Does anyone know? There's some numbers next to the oxygen. O2, that's how you put two oxygens together. But is it the 8th element? You'll see things like O8, and you'll even see something on top. You'll often see O8, 16. I actually already forgot. Does the 8 go on the left or on the right? I actually forgot. It's been too long since I actually took a chemistry class. I just know the way things work. I don't often know the numbers. But what this means is that there's like, is it on the right side? This is the 8th element. There's this thing called the periodic table of the elements, where you got like all these elements written down. So O happens to have what's called an atomic number of 8. That means it has 8 protons. And it has a atomic mass, usually 16. Left. People are saying left. That makes me feel better. And the reason is because on the right, I usually want to write how many of them there are. Thank you very much. Wait, now people are saying right? Both work. Now I'm confused. So I'm just going to say I'm a mathematician. I'm the kind of mathematician that sometimes divides by 10 cubed by multiplying by 10 cubed or something. But we got this, okay? Whether on the right or left doesn't really matter. But that's like 8. Now, the mass is 16. There's like 16 neutrons or protons inside there. But at the bottom of the periodic table, you don't find things that have like some number with a billion. You know what I mean? Like all the way at the bottom of the periodic table, you've got like some other things at the bottom, like, I don't know, uranium or something. I actually don't know what is uranium's atomic number, but I seem to remember that there's like a 238 for the atomic mass when you do this like nuclear fission. Is it 92? Actually, I'm just going to make this up. Is it 92? I'm just going off the top of my head now. This may or may not be right. I seem to vaguely remember uranium's 92 and plutonium is 94. But anyway, this is just showing you how my head works. 235 is the extremely like fissile, the dangerous kind of uranium. Okay, but the weights, it's not off by a factor of 10 to the power 5 or 6. That's only off by a factor of like 16. That's how I knew that my answer was wrong. That's how I knew that my calculation was wrong. I'm going to take one pause right here because actually I record all of these at the same time. I need to flip the card that's inside the recorder, and I'll be back with you in approximately 1 minute. Hang on tight. Hey everyone. Actually, what just happened was because I was just teaching a PhD level class at Carnegie Mellon, and I was teaching like the grand finale of something that they had just learned over the course of a few, like maybe a few weeks. And so we went way over time. And when we went way over time, the card recording that I was using was completely full. And so we were actually recording on a different card, and I just had to go and take that out of the computer and put it here. Okay, let's finish up this thing, which I had said earlier, because I just wanted to tie this whole thing together in a way that I didn't run out of time on the recorder. But my goal of showing you this was to show you that's the point of math. You see, that's the point of where math is useful. If you didn't have this sense of like, where does my mistake come from? You might have just gone and said the answer is there, we're done. And when we said we're done, we'd just been like, we just have said like, oh, I don't know, I guess it's just off. But it's very, very difficult to be off if you can control each source of your error. And I hope that by talking about chemistry or like atomic physics, this also has helped people to maybe see that if you do think about math, even when you do chemistry or physics, the world makes more sense. And in fact, as I look at this, that's how I know there can't be that super dense material, because I can't pack that many protons and neutrons together in the same nucleus. Uranium is basically at the bottom. There's like, I don't know, maybe another row or something below, maybe. I think it goes to like 110 these days, or maybe 112 or 115, but those atoms don't stay stable, they fall apart. Regardless, what we now see is that this way of thinking lets you see that you could not have the whole mistake come from saying that you use water to approximate the density of the materials in the earth. So to answer the question that you had asked, like, aren't there different materials in the earth? Of course there are. But the range of densities that we could have, it couldn't have gone from like water to something that's 1,000 times as dense as water. And so on average, I can just use 10 times as dense, where I just thought about like going to the gym. And this is an example of a Fermi problem, and hopefully it's also a nice lesson on how to use the math. Okay, what else can we do here? We got some more questions. Let's see. Oh my goodness. Now this one's going to be hard. So Jacqueline Zhou asks, how do you calculate the mass of the sun? Okay. Mass of the sun. If I wanted to do that, now that one is going to be pretty hard. I'm actually trying to think, like, what would I even know that I could use to try to figure this out? So, I know how far away. You see, the problem is the densities now are really, really bad. The problem is I actually don't know what is the density of the sun. So I guess what I'm thinking about is there any way that we could try to figure out density of a ball of gas? Yeah, so this is a good question. I mean, I'll say we know that the distance from the Earth to the sun, the distance from Earth to the sun is like 9 minutes of light. So we'd have to then use like the speed of light, 300 million meters per second, something like that, to go and find out how far away it is. Then you have to do something which you should not try at home, which is to hold up something at the sun and look at like what angle it makes. Then you'd find out like what is the diameter of the sun. So I'm telling you, like, there are ways that you could try to figure out the diameter of the sun by using the fact that there's this distance. And if you have this distance, then how could you figure out, like how big is the diameter? Then you could use the diameter to go and figure out the volume. And from the volume, we need to use some kind of approximation on the density. On the density, I actually don't have a good sense of what I would use, but I would say most likely the density would not. Yeah, I would probably just try to use something like what is the density of a gas, hydrogen. Because somehow if you pack it too closely together, yeah, it's hard to say because there's also this pressure question. Yeah, that's a good question. So has the sun ever been measured? I mean, these things are possible. I'm actually just trying to say, like, what are the different kinds of physics that I would use? If you're actually curious how you find the distance between the Earth and the sun, that is also very interesting. That happens to be, I guess these days, we can actually go and even put out satellites. But there are other ways that you could try to figure this out using the fact that there's some formulas about radiation. And the fact that the temperature on the Earth is what it is can actually tell you something about how far away the sun happens to be. But I'll say I don't actually have a good answer for you off the top of my head on this one. In fact, I think it's pretty interesting. So I don't know. I don't know. It's pretty interesting. You can use masses of helium and hydrogen gas, you're right, but the issue is that in the sun they are being compressed. So unfortunately, the issue is that we have actually quite a lot of compression on this hydrogen gas. Oh wait, there's another way, with gravity. No. So now I'm curious. Ah, yes, there is a way you can figure this out. Oh my gosh, how do you figure out the mass of the sun? With gravity. So what do I mean? So if I have a very heavy object, that makes it so that my rate of speed of falling is something. Okay, time for physics. I'm not sure I'll have the time to finish this whole thing today, but let me talk about like what I do. Yes, it has turned apparently into Ask Science Anything, but I hope that you have seen that this is something that is pretty interesting also to a mathematician. So, you know what gravity is? Gravity is something where it's like if I've gotten again, this is not like, don't think about it as the Earth. Think about it like out in the universe somewhere. If I have this big blob, I guess that blob is called the sun. If you have this big blob, the big blob attracts things towards it, and it has something called acceleration. So it's like if I've got something over here, by the way, that something is going to be called the Earth. That's going to be called the Earth. The sun attracts the Earth towards it at some kind of an acceleration. Actually, does anyone know what is the acceleration? Do I have any physicists here? Do I have any people here who did some physics? So I vaguely remember that somehow the gravitational force, the force of gravity, has a nice formula. It's G times one mass times the other mass over how far apart squared. So, yes, somebody's talking about the G on Earth, that 9.8 meters per second squared. There's another G, which is called the universal gravitational constant. And the universal gravitational constant is what you use whenever you have any two objects, not necessarily the Earth. So I'm just going to say, like, we're not going to work through all the numbers here. You could measure this G by getting two masses and seeing how much they attract each other. Okay, so there are ways to estimate that G. It's divided by r squared. That's related to like expanding things out. It's related to the fact that the surface area of something quadruples when you go out by twice the distance. That was actually a topic in our Daily Challenge Module 0 course. But so this happens to be the force that I'll use. If that's the force, there's an acceleration that it causes. So the force causes a certain acceleration to happen. So the acceleration caused by the gravity on your mass m, the acceleration on the mass m, force equals mass times acceleration. And so this is g times the mass of the sun divided by the distance squared. So I could actually figure out what is the acceleration that's pulling the Earth towards the sun. Now, why is that relevant? It's relevant because the Earth is obviously not crashing into the sun. The Earth is not crashing into the sun, or else we would all be dead by now. The Earth instead is going around. But it's going around. The reason it's going around is because it's actually always falling into the sun. And so what you can figure out, again, we're not going to do all of this in science today, but I'm just going to say, here's how I might figure it out. If you know how fast the Earth is moving, and you know how far away this is, you can figure out what is your acceleration going towards the center. Okay? So the point is like, if I know how far away this is, which is like 10 minutes or 9 minutes at 300 million meters per second, if I have that, I know what this distance is. I could figure out that r. If I can figure out this r, I also can then figure out how fast the Earth is moving because I go one full round in 365 days. Right? That's like 1 year. So at this point, I can figure out what is my speed. I can estimate the speed of the Earth as it's going in this line. I can estimate the speed. We call it velocity. But if you know the speed, and you also know the radius of the circle, you can figure out what is your acceleration causing you to turn. With that, I would go back into this and figure out the mass of the sun. So that's actually what my answer would be. JK says that you are actually a physics specialist and went to Stanford University. Well, welcome. It's a pleasure to have you. But I'm just going to talk through, I just wanted to talk through, this is what I would do. If I had, another hour or so, if I was somehow in ancient times and I didn't know any of these numbers, I would actually go and just figure out what is this acceleration that we have based on 365 days to go around and the distance, and we're good. You matter unless you multiply yourself by the speed of light. Then you energy. Eric Shen, you are very funny. Okay, that's hilarious. Okay, sorry, Yihong, if you're kind of confused. I think maybe I should stop talking about too much physics, other than saying that maybe you saw I got excited because I was like, hey, I could possibly figure that out. And what I just talked through is how somebody like Isaac Newton, if they wanted to figure this out, would actually start doing all the experiments and figure this out. Okay, more questions. What can we do here? Okay, let's see. Hi Bye has asked, what are the last 3 digits of 43 to the power of 100? 0, 0, 0. Okay, more questions. What else can we have here? Near asks, how can you explain how you use the Fourier transform to make the Corona app? I can after we release the Corona app. As soon as I finish this live stream, I'm going to be back programming again immediately. Hopefully we'll be done soon. Let's see. What else do we have here? I'm looking at the different sources of questions. Oh, why 0, 0, 0? Somebody asked what was 100 to the power 43, I think. And 100 to the power 43, that's going to have lots of zeros at the end because, well, it's just 1 with a lot of zeros. Okay, great. What else can we have here? Looking at all of these questions. Anne Joe asks, what's the Corona app for? What it's for is to help us all be able to stop being stuck at home for the next year. That's what it's for. I started thinking about this because I realized that if nothing is done, we will be all stuck at home or dying for the next year, and that's not acceptable. And so maybe you can also see, based on the way I've been talking and answering all these questions, my whole goal of this live stream is not to teach you one math topic. It's almost to show you how you can use mathematical thinking and like scientific knowledge and engineering knowledge to kind of figure out all kinds of things, the way that people like Newton, people like Galileo, people like Einstein, all of these people that we think of that have made great things. If you can think in these ways, you want to combine with all of those other knowledge, and then someday you have something to do, which is more than just a math test problem. So this particular live stream is always going to be full of these things where I get excited whenever I can go and start talking about, what we can do with all of this. Let's see. What else do we have here? I'm just looking through. Oh, somebody says not 100 to the 43. Someone wants the last 3 digits of 43 factorial? 0, 0, 0. That's also okay, because you've got enough 5s inside. Muffin asks, what language do you use in your programs/video games? Whatever you need to. So the way I have always felt is with a computer, I actually love working with computers because if you tell it to do something, it will do it. And it's actually the same way of thinking as what I just went through when I got that calculation error about the mass of the Earth. It's like, hang on a second, how in the world did that break? You may be used to thinking of computers as things that always break. Somehow, unfortunately, the technology often doesn't work great. But if you're actually the one programming it, and especially if you're programming it in a way where it really does everything you tell it to do, if it doesn't make what you want at the end, then you just go and figure out what's wrong. What languages do I use? When I was writing video games in school a long time ago, that was C++. These days, I would say that for a lot of things that I do with the internet, I will use Python and JavaScript. But when it comes to writing an Android app, they actually use Java. Some people on our team are using something called Kotlin. I guess I have to learn that too in order to collaborate with them. But my attitude always has been, if there's a source code, if there's a computer program that does something, and if that computer program is only like 500 lines long, I know that I can sit down and figure out exactly what it does. And that's actually how my job in this ended up being, figure out exactly how this core piece, which is using like all kinds of various like sensors of the phone to talk to each other, how does that work? And I will say that the mathematical background, if you go and keep learning math and keep learning how to think, that'll be really helpful. JK, Kotlin. I love Java and Python. Right, my attitude is like all these things are fun, but I hope that you're able to see that the goal is just like use this math to do something good. Chirag asks, can you explain how to prep for the AMC8? I can explain. The way to do that is to get used to doing problems that you don't know how to do. One way to do that is to go and play with old AMC8 problems. The other way to do that is if you can find a source of problems that's always going to be a little bit out of reach, then that would be the best way to do so. When I was learning these things, I just did problems like from old contests. I didn't have a systematic way. It works. But eventually, in these days, there are all different ways that you can find, sources of problems that will be just the right level for you, where you also learn something from it that's more efficient. What else can I see here? I'm looking at the different questions that we might have. Ryan Xiang says Scratch. That's actually a very useful way to learn how to program computers too. I just never learned that because that was after my time. Let's go back to math. I want to pull back to math to go and see what we can do here. I'm looking at all of these different questions that are here. These are kind of interesting. So I saw a question that's quite nifty. How to find the range of x to the power x? Wow. What's the range of x to the power x? I don't know. Maybe I'll start to draw it. What does it look like? Well, when x equals 0, I have 0 to the power 0. Not allowed. So let's not do that. But if I'm going to take another number, which is like 1 to the power 1, I can do. Let's start to graph this thing. 1 to the power, you know what? I want more space. So I'm going to make more space here. So this is 1, and this is 1. 1 to the power 1 is here. What is 2 to the power 2? Whoa, it flies all the way up, so it's not on the screen. How about other numbers? So let's do 1/2. So I'll say up here, it's going to go up. It's quite clear to people, I think, that it just goes up. The question was, what's the range of x to the power x? Meaning, what kind of numbers do you get as x to the power x? So you'll get every number from 1 and higher, that's for sure, because it's just going to go up, big slope, yes. How about 1/2 to the 1/2? What does that mean? 1/2 to the power 1/2. Well, that's the square root of 1/2, as we saw from other live streams in this week, which is 1 divided by the square root of 2. 1 divided by the square root of 2. The square root of 2 is approximately 1.414, and 1 divided by square root of 2 is approximately 0.707. The more math you do, the more you'll see this particular number. So 1/2 is going to be about 0.7. It'll be like this. And I'll say that if you actually went to draw this, what you'd find out is it would look something like this. It turns out that even though I don't allow 0 to the power 0, it turns out to be very close to 1. So it looks like this. So now the question is, what's the minimum of that? So the answer to this is, it turns out that logarithms are useful. And because I know that a lot of the people in this audience have not taken logarithms, I will just say this in like 10 seconds. And then if you happen to know about that, you can solve it with that. X to the power x is equal to e to the power log of x, ln of x, raised to the power x, which is e to the power x log x. Now the question becomes, just find the range of that and take e to the power that. If I know that my range is going from e to the power 0.5 up to e to the power infinity, or like forever, the minimum is e to the power 0.5. Okay, how to find range of x log x? Actually, you can do this. You do it with something called calculus and the derivative. In fact, the derivative of x log x you can do. You could actually figure this out. If f of x is equal to x log x, the derivative of x is equal to log x plus x times 1. X times 1 over x, which is 1. And you could go and figure out when that happens to be 0. That happens to be 0 when x is 1 over e. Whoa, is it that easy? So x is 1 over e, right? I'm sorry if you don't understand this. I will just say that equals 0 when x equals 1 over e. And so if that happens to be the smallest that it is, then it looks like the answer up here, I'm just going to give you an answer and we can see if that was right. The answer should be e to the power 1 over e minus 1, so like that. That would be my guess. E to the power minus 1 over e. I don't know if I'm right or not. Maybe it's right, maybe it's not right. But in any case, why I went through this is to say, here's how you draw something. This is why learning pre-calculus is useful, or algebra 2 is useful. That lets you take something messy like x to the power x, and the x to the power x you rewrite with these e's. Now, once you have e's, that turns out that calculus happens to be useful. By the way, if somebody actually can look up whether the answer is right or not, Will from Alpha would probably know. But in any case, it's like, you do this, like this particular piece, derivatives exist. That's calculus. You do this and you're done. Okay, great. So again, I understand that this is probably a more sophisticated question than we were expecting in this live stream, but as usual, I wanted to show all of these different angles. Let's finish one more. Let's see if there's one more question. Philip Neller asked, how many ways are there to find the next number in the Fibonacci sequence? A lot. There are a lot of ways to do anything with Fibonacci. With Fibonacci, you can use, like, there's a formula you can use to figure it out. Actually, I have a lecture that's now online. It was something I was giving to math teachers. And that was something for Math for America about like a week ago or something. And if you look for that, that's like a 2-hour thing on YouTube. And it talks about Fibonacci numbers and ways that you could even calculate out the like nth Fibonacci number yourself. But there's lots of ways, and the most important thing is just to be creative how you do with what you do with mathematics. My hope with this live stream is that we were able to take a lot of people through quite a wide tour that went through some math problems, some uses of mathematics, even touched on something which is significantly more advanced. As usual, we hope that more people are going to come. Do I like cheese, Joshua Wang? The answer is yes, I do like cheese. But I developed a liking for cheese after I spent a year in England. I was at Cambridge, England, studying for a year. The same place that Newton once was, which is an inspiration. And maybe that's a good place to end, which is to say, if you know anyone else who might benefit from or who might enjoy seeing like a discussion that will range throughout all of mathematics and science, and where you actually get to see in real time live how somebody who maybe has a background in mathematics and science tries to reason through these questions that come from all over the audience, please do spread the word. We are hoping that this can reach more and more people to show people that when you learn about math, you can learn about all these other angles as well. With that, I'm going to wish all of you the best. I hope that you have as good a day as we can have in these days, and I hope you'll also be hearing some interesting things from our team soon. See you next time.